Assalamu alaikum warahmatullah. Welcome to this fifth lecture of our subject mechanical vibrations, and this lecture is actually for the last week. I had recorded that, but due to some trouble, I was not able to upload that, and there were some errors in that one. So I'm recording it again, and I'll also be uploading the new week, this week's lecture, that's at week number 6, as well as the assignment for you guys to have a try. So, we have discussed so far the what the system dynamics was, what is a mechanical vibration, how you can classify the mechanical vibration based on its material properties, based on the degree of freedom, based on the linear or the non-linear systems, time invariant, time variant systems. We have seen this in detail in the last lecture. Then we had discussed how to approach a mechanical vibration problem. The first was to understand the system based on the types of system we have discussed, then to generate a model for that system, mathematical model, and then drive the equation of motion for the based on that mathematical model, and then perform the solution. So we haven't touched the solution part yet. We are into understanding different types of system and driving the equation of motions. And we have seen there are different ways to drive the equation of motion. I'm not going to discuss that again. You can refer to the last lecture. What are the different ways we can approach a different to approach the equation of motion of a same system using the different techniques, and each one has its own benefits and drawbacks. So in the last lecture, we saw 1 degree of freedom free vibration system. Uh, we are discussing briefly. So in this lecture, we are going to focus on 1 degree of freedom free vibration system with damping, and there are two different types of damping: viscous damping and the Coulomb damping. You will see. And obviously, when there's a damping, we know what the damper does. A damper dissipates the energy. It takes the energy out of a system, any system that is vibrating. So it means after some time, there will be a reduction in the vibration amplitude, and slowly the system will move towards rest. And after some time, it will become steady. So this is what we call logarithmic decrement. So there's a decrement. Let's say you have a vibration of a system going on, so because of damping it will reduce slowly, and after some time it will come to rest. So this decrement, that's called the logarithmic decrement. So we will see how we can quantify this decrement in the vibrating system. And the third one, we will see 1 degree of freedom again, but the force vibration. So not a free vibration anymore, but a force vibration. So that solution of that one, the method of driving the equation of motion for that is called the complete solution method, and we'll see what it is we will see later. So first of all, you should be aware of difference between the free vibration and the force vibration. Free vibrations and the force vibrations. That's a force vibration. So we will discuss with the free vibration just to give a brief idea of what are the difference between them, and the force vibration, because we will be using this term again and again, and sometimes student gets confused. If there is no force in the free vibration, how come the system is vibrating? So it's simple. Let's say you have a mass spring damper system. So if before you start to observe the force, if there were if the at the time before when you start to observe the force, there is no force, F equals to 0, then it will term as free vibration. What does it mean? Let's say you just excite the system and then you remove the force, and then you start observing the vibration of a system. Let's say the force was applied 1 Newton from at t less than 0. So before you start observing the motion of the system, the force was applied and it removed, and then force is equal to 0 at t equals to 0 to, let's say, 10 seconds. So then once you start observing the motion of the system, the force was removed. So now you have given initial excitation to the system, and now you're just observing how the system naturally vibrates and how it dissipates the energy. That's kind of a free vibration. But if you apply the force, let's say 1 Newton, and you are simultaneously observing the system as well, then that's a force vibration. So you are applying the force and you are also observing the motion of the system, and you're analyzing its response, steady state or the transient response. So that's the force vibration. So this force can be step force, ramp force, it can be sinusoidal for periodic force. We will see that later. Now let's jump towards our first topic, that's the 1 degree of freedom, 1 DOF free vibration system with viscous damping. So again, we'll just see the different cases of this one. So let's say again we have this 1 degree of freedom system. We have derived this earlier. I'm just going to quickly write down equation of motion so that we can move forward. Let's say there's a spring with a spring constant K. We'll call it spring constant. And the C, that is the damping constant. And once it was excited in a free vibration, so our equation of motion will be mx double dot plus cx dot plus kx. I'm not going to explain how come the equation of motion is this. We have discussed this in the last lecture. Then we said like there are different ways we can solve this one, and currently we are dealing with only the general solution method, means solution method of a differential equation. We are not discussing any other method at the moment. Although we will start Laplace transformation from the next lecture. So we said like, because that's a second order differential equation, so the general solution for such equation is x of t equals to, name any very constant value, let's say a exponent s of t, or you can call it lambda t, as we have seen, as we have marked in the last lecture. Call it lambda t, whatever you like. Just make sure it doesn't mix up with any other variable or constant value that you mentioned. Then you can take first derivative, and you can take double derivative of this. We have seen this one in the last lecture, a lambda e lambda t and a lambda square e exponent lambda t. And now when you start substituting this one into this equation 1, so you will have a kind of a quadratic equation that becomes a lambda square e exponent lambda t plus c a lambda e exponent lambda t plus kx. So the k into a e exponent lambda t whole equals to 0. We can take out this, sorry, we can take out a e exponent lambda t as common value. So we will have a e exponent lambda t as a common, so it will become m lambda square plus c lambda plus k equals to 0. So either a e exponent lambda t equals to 0, or m lambda square plus c lambda plus k equals to 0. So both are the solution. We are not interested in this one. We call it trivial solution. That means it's useless for us. It's not important for us. So we are more interested in this equation because it involves the dynamics of our system. That's a stiffness, damping, inertia, while this equation doesn't tell us those things at the moment. So now that's a general quadratic equation. You can apply the quadratic formula to find the value of lambda, and you know the famous quadratic formula. You can just directly apply minus c plus minus under root c square minus 4mk divided by 2m. You can simplify this one, thus minus c over 2m plus minus under root c square, c over 2m square. Let's erase this one, c over 2m square minus k over m. That's a simple mathematics. I just took 2m into the under root. And from here you can have the two different solutions. You can find the roots of this equation. Now if you just substitute these values of these roots value, you can lambda 1 and lambda 2 with the both plus minus, you can substitute this in a general equation. The total solution, that is x of t equals to a1 e lambda 1 of t plus a2 e exponent lambda 2t. So now we can substitute lambda 1 and lambda 2 in this equation. So it will become a1 e exponent lambda 1t, that is whole minus c over 2m, that's plus under root c over 2m square minus k over m, and that's whole into t. Sorry, t is in, and plus a2 e exponent lambda 2t, that's whole value with the negative sign. It become minus c over 2m minus of c over 2m square minus k over m into t. So that's the total solution, where a1 and a2 are constant values. They can be determined using initial condition. What do we mean by initial condition? What was the state of system at the beginning of the motion? Let's say, what was the position of a system at time t equal to 0? What was the position of a system? Let's say x, any value. What was the velocity of a system at time t equals to 0? Let's say x meter per second square and meters. So these are the initial condition. You can substitute, you can again substitute t equals to 0 in this whole equation and find out the roots, or find out these values of a1 and a2. You can substitute, you can take the derivative of this whole equation and substitute this value into that one, and you will see that later on. Now this roots value, they tells us a lot of things. So there's a thing called critical damping. So there's a thing called critical damping. So this is the amount of damping that allows system to return to its equilibrium position as quickly as possible without oscillating after being disturbed. So let's say if the damping constant that we have, let's select this one, we know C is a damping constant, and Cc is a critical damping constant. Critical damping constant. So what happens with critical damping? In the critical damping, the value under the root, that is C over 2m minus km, that becomes equal to 0. So for the value of C, for any value of C, if this value whole of this expression becomes 0, that's the value of critical damping. We call it radical becomes equals to 0. So from here we can find out how to determine the critical damping value for any system. So obviously you can take this on the other side, k over m, take square root on both sides, it becomes cc over 2m equals to under root k over m, and cc equals to 2m under root k over m. And we know this k over m is a natural frequency of a system. So we can write it as cc equals to 2m omega n. So in order to find a critical damping value of any system, If you know its mass, if you know its natural frequency, you can find what amount of damping you need to keep the system stable, to avoid any oscillations in our system. Uh, our another, because the mechanical vibration has a lot of mathematics involved, so and to easily represent the system and to easily represent the change in the behavior of a system with respect to different changes in its properties, we try to use a dimensionless number, so because it simplifies a lot of calculation. So there's a term called damping coefficient, that's called the damping ratio. So that's represented like this. It's not a very good one, so I don't like to draw this, but it's really weird. It's like, that's called the damping ratio, and it's equals to the damping constant divided by critical damping constant. So what we do, we draw the graphs of system behavior based on the changing damping ratio. Obviously, the critical damping value is constant for any system because the mass is constant and because every system has a fixed natural frequency. So you can keep on changing the value of C that you can physically or practically provide to your system, and you can observe the change in the behavior of a system. So this is why we define the system in the terms of damping ratio as a dimensionless quantity. So now you can even simplify the system further using the damping ratio. So we know C over 2m, it's equals to C over CC, sorry, C over CC into CC by 2m. Just simply multiplying divided by the C critical damping constant. So C over CC will become the damping ratio. So we can write it as into omega n. So this is how you can represent the system in terms of damping ratio. So we can further rewrite these roots of our equation, this one in terms of damping ratio as well. So it will become lambda 1 and 2, it will become minus of damping ratio plus minus under root, again the damping ratio, square minus 1, and this whole multiplied by omega n. That's natural frequency. So that values of lambda that can be rewrite in terms of these roots, that can be rewrite in terms of damping ratio, this one. Now based on this, we have different cases for the mass spring damper system. The case 1, that's called an underdamped system. So an underdamped system, it's a vibrating mechanical system in which the damping is not sufficient to prevent any oscillation. So the system, when it is excited, it vibrates for some time and it's gradually loses some energy until it reaches to the steady state condition. So our system do vibrate, but it takes time for system to reach the steady state condition. So in this one, system oscillate, amplitude of the vibration decreases exponentially, slowly with the time, energy decreases with some time, and it has some application as well. So we'll see that later. So in underdamped system, when the system is called underdamped system, if the value of this damping coefficient is less than 1, or it can be also written as the damping constant value is less than the critical damping constant, or you can also write, because in different books you will find a different way, or if C over 2m is less than under root k over m. All of these are condition of critical underdamped system. So either you can say the damping ratio is less than 1, or you can say obviously C is less than C over C, that is why the damping ratio is less than 1. Or you can write it as this one. All of them are same, means the same. So you can say upon excitation, system vibrates for some time before uh, equilibrium condition, all those before losing some energy and reaches a steady state condition, equilibrium condition. Obviously steady state has a broader meaning. Not every steady system is a steady state. So these are the conditions of the the underdamped system. So uh, if lambda is damping ratio is less than 1, so obviously this value is less than 1, it's negative. And when you, let's say it's 0 0.9, 0.9 square, it's still less than 1, and this whole value will become an imaginary number because it will become negative. So we rewrite this as minus damping ratio plus iota, that's the imaginary number, 1 minus damping ratio square into omega n. I'll be more focusing on the physical intuition or physical explanation of the system, because you can follow up this mathematics. I will share the notes so you can follow these mathematics. I have explained the fundamentals of this, so it won't be difficult for you to follow up, but I will try to explain the physical meaning behind all of these equations so that you can live this subjects. You can understand what's going on behind these equations. And same is the case for the lambda 2, it will become minus damping ratio minus iota 1 minus square damping ratio square into omega n. That's another rule, and you can again substitute this root in your equation and solve it. So I'm not going into the solution at the moment, uh, except for probably, okay, we'll solve this one. So once you substitute this equation into the main equation that we had, the general solution, that's called the general solution. So a x of t, a1 e exponent lambda 1t plus a2 e exponent lambda 2t. So if we rewrite this equation, x of t a1 e exponent lambda 1 of t plus a2 e exponent lambda 2 of t, and you can substitute these values of lambda 1 and lambda 2 in this equation. So you will have at the end, and picking out common from this one, so you will end up with e exponent minus damping ratio omega nt, and in the bracket would be a1 e iota 1 minus damping ratio square into omega n of t plus a2 e exponent minus iota into 1 minus damping ratio square into omega n of t. So that's the solution for this one. You can even simplify it further, and from the Euler's formula, because this itself, it becomes a condition of e exponent iota omega t, or e exponent negative of iota omega t. So we know e exponent iota omega t is equals to cos of omega t plus iota sine of omega t. So we can substitute this one, we can use this formula to expand these, and so it will become E exponent this damping ratio omega n of t, and then we have a, you can just write and simplify this. I'm going to directly write the steps. So it will become a1 plus a2. I'm just merging the cos of both and sin of both. So it will become a1 plus a2 cosine of omega t, that is 1 minus damping ratio square. That's a weird damping ratio. I'll just again. It's under root 1 minus omega square omega nt plus iota a1 minus a2 into sine 1 minus omega damping ratio square omega nt. So that's how you can simplify this formula, this solution method, and you can even, if you want, you can even simplify it further. So just maybe simplify it, because these both are constant values. Just call it maybe a1 prime. Just call it a2 prime, because they both are constant values, so we are designating them with a new constant value. It doesn't make any difference for us. So x of t is equals to e exponent minus damping ratio omega nt. It becomes a1 prime into cosine of 1 minus damping ratio square omega nt plus iota a2 prime sine of 1 minus damping ratio square omega n of t. Now you can even solve it further and write it as in the sine and cosine form. So if we move towards our, just copy whatever we have here. So from here you can just write the general solution by reducing it further. It become x naught e exponent minus damping ratio. I really don't like to make it again and again. Damping ratio omega n of t into sine of 1 minus damping ratio square omega nt plus phi naught, that's phase. We have represented this as a phase, or you can write this, or you can write it this in a cosine form, that is x e exponent minus of damping ratio, sorry, e exponent minus of damping ratio omega nt cosine of 1 minus under root 1 minus damping ratio square omega nt minus of phi. So they both are the general solution of this system, and we can find obviously this x naught through c1 and other constant using the initial conditions. So this is how we can find in this one. You can even in this whole equation we can simplify it further. This itself is called as omega d, that is damped natural frequency. So this is damped natural frequency, which is equals to omega n into 1 minus damping ratio square. So you can write it as cosine omega dt minus phi, or sine omega dt plus phi. So this expression itself is called as damped natural frequency. So what will be the natural frequency of system once this damping is added? And it will always be less than the omega n. So omega dimensional frequency will always be less than omega. That was a general solution method for just to show you how you can proceed with the solution of 1 degree of freedom vibration system using general solution method. And so, but if you see, I don't know if we have it, okay, but if you see here, if you draw the vibration pattern of a damped natural system, let's say it start vibrating from here. After some time, it will start to reduce the vibration, and so on and so forth. So that's an underdamped system. So there are some other systems as well. Let's say if your system was critically damped. So in the critical damped system, there would not have been an oscillation. So it would directly reaches to the steady state or the rest position. That's a critical damp. And then there's some overdamped system. Then there's some overdamped system which led system to oscillate a large amplitude and then slowly reaches the rest position. It also ensures that there is no vibration, but it takes time compared to the critical time system. Now looking at the case 2, I just explained all of these cases. So case 1 was underdamped, case 2 is critical damped. And I've already explained this while defining the critical damping of the system. So if sorry C becomes equal to CC, or damping ratio is equals to 1, because C is equal to CC, the damping ratio will be equals to 1. Or you can say C over 2m is equals to under root k over m. Then all of these are conditions for the critical damping system. So in that case, if C under root 2m, because we know what was our roots, general roots of our system, I'm just going to rewrite this one. So we know if C over 2m becomes equal to km, then this whole part would be equals to 0. This becomes equal to 0. It becomes 0 because C over 2m equals to k over m. Only thing we are left with is a real component, that's C over 2m only. So lambda 1 would be equals to lambda 2 equals to minus C over 2m, because the C is now equal to critical damping constant, which can be written as minus of omega n natural frequency. So in that case, the solution of our system, it becomes A1 plus A2 t e exponent minus of omega n t. And why there's a t here when the roots are same? That's the solution of differential equation you must have studied in your calculus. So whenever both roots are equal, we add t here, a1 plus a2t into exponent minus n omega n of t. So again, that's the solution of the critical damping system, critically damped system. Now the last one would be the overdamped system. So what happens when the system is overdamped? That's case 3. So in the case overdamped system, the damping ratio is greater than 1, means the damping we are providing is larger than the critical damping of a system, right? Or C is greater than CC, right? Or you can say C over 2m is greater than under root k over m. All of these are conditions of the critical overdamped system. So in this case, the roots will always be real. There won't be any imaginary roots. So lambda 1 would be equals to minus of, or if you can just rewrite the same. So say C over 2m is always greater than kmm, k by over m. So it means this this component will always be the real value. There won't be iota involved. There won't be any imaginary number, because if C over 2m is less than k over m, it means this whole value will be negative, and then you will have an iota imaginary number at the outside the roots. So but in this case it's always real. You can even write it as lambda 1 2 minus of damping coefficient plus minus under root damping coefficient square minus 1, and this whole equals to omega n. And now you can write this in the general solution style, general solution method. That's a1 e exponent minus of damping ratio plus under root damping ratio square minus 1 into omega n of t, natural frequency of t, plus a2 e exponent minus of damping ratio minus of under root damping ratio square minus 1 omega n of t. That's again the general solution method of critically overdamped system, and again it does have its own significance. So all of these three cases have their own uh, applications and the physical intuition. So you can say physical explanation and in the real world. So for say underdamped system, and then we have critically damped system, and we have overdamped system. So for the underdamped system, it has no energy loss, no energy loss, or there's apparently no or very little friction, so it vibrates for a lot of cycles before coming to rest. It vibrates a lot of cycles before resting. I'll just erase this one. What else we can explain for this one? uh, Theoretically, total mechanical, if there's no damping, under damp can be that no damping or very little damping to the damping in just at the boundaries. So the mechanical energy loss is very little. It remains almost constant in some cases. So what are the application for this one is you can say ideal pendulum, which is an ideal case, or we can have some atomic vibrations at the atomic scale. Apparently there's no vibration because there's no continuum. So when the atom vibrates about its position, we know the to and fro motion atoms is vibrating about its position. So apparently there's no damping involved for those atoms, so they kept on vibrating for infinity. And same is the case if you have an ideal pendulum that's vibrating, so it will keep on vibrating. Or even if it has a damping, it will be very less. So it will vibrate for a lot of cycles before coming to rest. Then we have critically damped system, which has enough damping to prevent oscillations and to stop it within the time frame we need. So it has a lot of application. That is maybe the car shock absorber. So whenever your car passes through a road bump, and those road bumps apply force onto your car, and that force is transmitted to the body, and you are sitting inside the car. So they add a damping system here, which makes sure that the the energy loss in a given time, so that vibration is not transmitted to the passenger sitting inside or the driver driving the car, so that you don't feel the vibration while driving your car. uh, Another crude example can be door. When you close the door, you expect the door to stop immediately instead of vibrating few cycles and then coming to rest. Nobody wants such door. Another, shock absorber, suspension system. In the big machineries, you have uh, the underground shock absorbers. So that is also kind of a critical dam system, not the overdam. Sorry, critical dam system. And for the case of the overdam system, we may have a lot of different examples like hydraulic systems and seismic vibration though in buildings. So there's a earthquake-proof buildings structures. So if you have a building, and so they add the structure, and they add shock absorbers here under the building. So the purpose of this shock absorber is, once earthquake starts shaking the whole building, so they absorb the energy, uh, and let not the building vibrate for a long period of time. So they let the building displace a bit. They don't want to stop it immediately, because it will give kind of a shock to the structure itself, and that may result in the fracture or the cracks in the structure. So they let it displace a bit, but not vibrate or go under cycles of vibrations. So that's an overdam system. Or maybe you can use the hydraulic systems, heavy hydraulic systems, industrial level, that are also overdam systems, and we'll see some examples for this one. So that's all for the 1 degree of freedom vibration system, and how you can reach the solution, and how there are different cases of vibration. Although we can just simply solve the mathematical equation and get some answers, but these cases that we have just discussed, they give you physical explanation of what's happening to your system when you change the value of k, when you change the value of mass, when you change the value of damping. Mostly we are concerned with the damping because the mass and the stiffness of a system is beyond our control. It is a material property, it's a structure property. You can't mostly play with those values. The thing we can play with most is the damping, so that's why we classify the system based on the damping. So this was explanation of 1 degree of freedom system with damping, and then the damping we were dealing with was viscous damping. So viscous damping is this kind of a viscous fluid that is absorbing the energy and dissipating it. Another damping that is used in the vibrating system is the Coulomb damping, and it is the case where the loss of energy of a vibrating system is done through the friction effects. So maybe the system is vibrating over any other structure and causing friction, and that friction is dissipating the energy in the form of heat. So that's another kind of damping. So there the damping will be based on not the viscosity of the fluid, but rather it will be based on the friction coefficient between the two materials. So that's a Coulomb damping, and we will see later on.